Okay, question 53. Delete in binary search tree. Delete the target key K in the given binary search tree. If the binary search tree contains K, return the root of the binary search tree. Find your own way to delete the node from the binary search tree. After deletion, the binary search tree's property should be maintained. Okay, so basically right now, we have a binary search tree and we need to delete one of the nodes. And after deleted, we need to, of course, update the tree and then return the root. Okay, so now looking into the function signature. The name of the function is delete tree, and the input type is a tree node for the root, and also the second input data is an integer for the key, and the output data is a tree node. So basically, the root of the revised tree. Okay, and possible corner case is when the root is null, then we can just return null. Okay, and then the solution here is that we can first use recursion to basically find the target. And for the recursion, we need to first define the subproblem. So we basically call the function itself, and then we provide the left kit or the right kit. And when the key is small, then that means we give the left kit, and then we need to update the left tree and then connect back to the root. And if the key is big, then we need to update the right tree and connect back to the root. Okay, and in order to update the trial tree, then we need to understand that there are three situations for us, and we need to have 3 ways to update the tree. So the first situation is when the target node has no kit or only has 1 kit, then you can easily update a relationship. And the second situation is when you have 2 kit, the target node has a 2 kit, but the right kit has no left kit. Then you can basically have the right kit to take it over the target's left kit. So again, it's just update the relationship. And the third situation is you have 2 kits and you have too many kits, like grain kits. Then we can set up a helper function, delete small, and then to basically find the smallest node from the right subtree, and then this smallest node will become the replacing node for the target node. And so this new replacing node will take it over the target's left tree and the right tree. And also, before we move this replacing node up, we also need to make sure its child need to be taken off. Okay, so we will go through detail later. Okay, now looking into the code. So first, signature, delete tree, and input is tree node, integer key, and output is a tree node. And first is sanity check. When the root is null, then we just return the root. And the next step is the recursion rule. We basically will compare the key with the root key, and if the key is smaller, then we know we need to update the left tree. So we set the root.left equal to the function itself, and then we'll provide the left kit and the key. And at the end, we return the root. And if the key is bigger, then we need to update the right subtree, and then we call the function and provide the right kit and then kit, at the end return root. Okay, so next here is when we already find the target node, then we need to update the tree. Then as I just mentioned, there are 3 situations. First, when you don't have a kit or you have only 1 kit, then so basically you check, okay, if the root.left is null, so target has no left kit, then you just return target's right kit. And if the target's right kit is null, then you just return target's left kit. And another situation is when you have 2 kits and the right kit is no left kit, then you just have the right kit to take over the target's left kit. So here you will say root.right.left is root.left. Okay, and then return root.right. Okay, so and the third situation is when you have 2 kits, and now you need to find the smallest kit from your right subtree. And then you have that to take over your left kit and right kit. And then you just return this, the replacing node. And so here we use a helper function. The helper function is delete small, and the input type is a tree node. And we provide the target's right kit here. And then the output type is a tree node. So to find the smallest one, first we set up the pointer, pre, and the cur. The reason why we need to remember the pre is that because at the end we need to delete the smallest node. Then we need to basically connect the parent of the smallest node to its kit. Okay, so now we have the pointer here, and then we continue to move the current pointer to the left. Basically, we need to find the leftmost kit. So the condition while loop here is when the cur.left is not null, meaning it's not the leftmost kit, then you continue to go left. Then you will update the pointer pre to the cur and then cur to the cur.left. And then after we find the leftmost kit, then we need to make sure that its right kit will be taken care of. So we basically set, the we basically connect smallest node's parent to its kit. So that's why we have the pre.left to the pre.left.right. Okay, at the end we just return this smallest node. That would be the replacing node for the target node. Okay, so then we come back here. So then here we get the smallest node, and then we take over the target node's left kit and right kit, and then we just return the new updated subtree. And then at the end here, we will connect it back to the root. So overall, the time complexity is all high because overall we need to basically all high to find a target, and also we need to also find perhaps have the all high to find the smallest node among the target's right subtree. So it's kind of 2 log n and then not log n, the all high. So overall is all high. Okay, and the space complexity is all high. Okay.